Hello everyone, this video covers section 18.8 power series. Before we go there, so far in 11, technically so far from sections 11.2 to 11.7, we talk about series. So remember, this is a series. And what we did is we have several tests to determine whether it was convergent. Remember that we use this for convergent, and this is for divergent. And remember, convergent pretty much meant that the sum was less than infinity, and divergent that it was equals to infinity. And we use several tests to do this. We use the integral test, the alternating series test. The integral test, remember, give us the P series. Okay. So they give us the P series, the alternating series test, and we also have the ones that I say were probably the most important ones: the ratio and the root test. There is also the comparison test, and so forth. So all of these were used to determine if a series was convergent or divergent. Okay. Now we're gonna go to power series. So power, you should think of technically just adding x in here. So now you have to be careful to keep track of which one is the variable and which one is the constant. So notice here, the variable is n, because n is going from 1 to infinity, and x is a specific value. And everything we're going to do from now on in chapter 11 is going to deal with power series. So power series has the following form, which is very similar to a series. That's why it's called power series, except that it has this extra part. Okay, and the reason why it's called power is because this is to the n power. Okay? And this is going to be called the power series center at a. Okay, at x equals to a, which is this. Okay, so notice the x minus a. The one we're going to deal most at the beginning is if a is equals to 0, well, then the series is going to be written like this: n equals to 1 to infinity, cn x to the n. So that will be the series centered at a. Now the goal is the same as when you did a series. We want to see if this is convergent or divergent, but now notice that you have an extra variable here, x. So therefore, what we're going to worry about is for which values of x is this going to be convergent, or for which values is going to be divergent. And this is going to be related 100% to one of these tests, okay? And usually we're going to deal with the ratio and the root test first, but all of these tests can be applied too. All right, so let's look to the next theorem or result. There's only three things that can happen here. The first one is the series converges only for x equals to a. And that's not very interesting, but that happens. That's number one. Now, the second thing that can happen is the series convergence for all values of x. So that the series converges for all x values. Now, here x is technically going to be the domain of a function, because this is going to be at the end a function of x. So you can think of this as the domain, and all x values means that it's going to be from minus infinity to infinity. Now the third case that could happen, and this is the one that will require the most work, is that there exists a value r which is positive, such that if this is less than r, then this will be convergent, and if this is greater than r, then it would be divergent. Okay, so here r is going to be called the radius of convergence. convergence, and we're gonna need I, which is gonna be called the interval of convergence. Okay, and the interval of convergence you can think also as the domain. So in this particular case, then this will be the interval of convergence, which will be everything from minus infinity to infinity. The reason why it's called radius and interval convergence is this: if you have x minus a is less than r, notice that this is the same thing as minus r less than x minus a less than r. That's from algebra. This is minus r minus a less than x, and this will be less than a plus. This should be a plus r, and technically this is a radius in one dimension, so you move it around, it will be a radius in two dimensions. So this will be a plus r, and this will be a minus r. So from here to here it will be convergent, and in here and in here it will be divergent. Okay, now the reason why this method takes longer is that the radius of convergence tells you, yeah, it is possible that is convergent. I mean, that is converging here, but it could also be the case that is convergent also at the endpoints, which will be right here. So you also have to check the endpoints, which will be this and this. So those are the endpoints, and for that you need to use another test. So this one usually requires two tests. Okay, and the first example we do is going to be like that. All right, so let's try this example. So here notice that Cn is equals to negative 1 to the n over n squared, and obviously the value for for a in here is equals to 0, okay, because you have x to the n, which is the same thing as x minus 0 to the n. Okay. So we're gonna use the ratio test. So we're gonna call now an the whole thing minus 1 over n, then x to the n. And when we use the ratio test, we use the absolute value, so you don't have to worry about the negative signs. So therefore, if this is the case, well, then the absolute value of an plus 1 is going to be x to the n plus 1 over n plus 1 squared, okay? Which, if you simplify more, this is x to the n times x, and on the bottom this is n squared plus 2n plus 1, okay? So therefore, if we do the ratio of an plus 1 over an, and we did this multiple times before, so an plus 1, remember, is x to the n times x divided by n squared plus 2n plus 1, and then an, it will be n squared over x to the n. Remember that all of this has the absolute value. In this case, this will cancel, and don't forget that we are taking the limit with respect to n, okay? So x for now is technically a constant, and this is what you have. You don't need the absolute value for n because n is always positive, okay? So then we take the limit as n goes to infinity of the ratio, because we're using the ratio test, and the limit will be x, then we're taking the limit of this, so let me write the whole thing. So therefore this is the limit as n goes to infinity of the value of x times n squared over n squared plus n plus 1. Notice that these two have the same degree, so therefore the limit of this is equals to 1. So therefore the limit is the absolute value of x times 1. Now remember that the ratio test requires that the limit to be less than 1 to be convergent. So therefore that implies this has to be less than 1. So if you want it to be convergent by the ratio test. Okay? So therefore this will be the radius of convergence. So R will be 1. And then the interval of convergence. So this is the part that, remember, if this is not everything or 0, then you usually have to do more work. So far, this is what we know before we find the interval of convergence. We know that no matter what, this is going to be true between -1 and 1. So far, we know this works. But then we had to check the endpoints. And the endpoints are the following. X equals to -1, which is this one. And then x equals to 1, which is the other one. Okay? All right, so what happens if x equals to -1? So we had to go back to the original problem, and at -1, this is what we have. We have the summation from n equals to 1 to infinity, -1 to the n, and then if x is -1, this will be negative x over n squared. Okay, so all you have to do is literally plug in x in here. Now notice that this is the same thing as, this is, by the way, to the n power 2. So notice the -1 to the n, that's -1 to the n, the same thing as -1 to the 2n, which is going to be always 1, because this is even, so this always will be 1. So therefore, this is the same thing as the summation from n equals to 1 to infinity, or just 1 over n squared. And based on what we did before, this is convergent because this is a p series where p is equals to 2 and is more than 1. Okay, so that's that part. Now, if x is equals to 1, then we're going to end up with the following series. N equals to 1 to infinity, -1 to the n, 1 to the n. And notice that this one is going to be the sum from n equals to 1 to infinity, or -1 to the n, or n squared. This one is also convergent by the alternating series test, okay? Because this one is changing from negative to positive and it's going down. So now we can see that this side now, so this one is actually okay, the endpoint, and this one is also okay. So therefore, the interval of convergence is going to be from -1 to 1 instead of -1 to 1. So if this would fail, then this would have to be a parenthesis, and if this would fail, this would have to be a parenthesis. Okay, so the interval of convergence could have, at the very least, they will have parentheses, and at the best, they will have brackets. Okay. All right, so let's try another example. Here, an is equals to x to the n over n factorial. Therefore, an plus 1 is going to be x to the n plus 1 over n plus 1 factorial, which you simplify, this is x to the n times x. And remember, this is n plus 1 times n factorial. Okay? It's always a good idea to factor or simplify before you plug it in. Right, so therefore, if we do the ratio of an plus 1 over an, this will be x to the n times x over n plus 1 times n factorial times n factorial over x to the n, and don't forget the absolute value. Right, so here this will cancel that, and this will cancel this. So notice that you end up with just the absolute value of x times 1 over n plus 1. Okay, so that's what you have. So therefore, the limit as n goes to infinity of the ratio is going to be x, because that doesn't depend on n, times the limit as n goes to infinity of 1 over n plus 1. Now, obviously, this limit, since you're dividing by infinity, is equals to 0. So this will be the alpha value of x times 0, which is equals to 0. This is always less than 1, regardless of the value of x. So therefore, this means this is convergent for all the real numbers. So this implies it's convergence for all values of x. So therefore, that implies that the interval of their radius of convergence is infinity, and the interval of convergence is from minus infinity to infinity, which again, remember, this is the domain, which means this works for any value of x. Okay. All right, let's try one more example, and this time we're going to use the root test. So here we have an is equals to 3x minus 1 to the n power divided by n cubed. So therefore, if you take the n root of this, remember, don't forget the absolute value. This will give you the absolute value of 3x minus 1 divided by n to the 3 over n. Okay? And recall, because this is the key to making the problem easier, that the limit as n goes to infinity of n over any constant over n, this is from calculus 1, that this is equals to 1. Okay? All right, so therefore, the limit as n goes to infinity or the n root of a to the n is going to be the same thing as the limit as n goes to infinity of 3x minus 1 over n cubed over n. And again, you can take this one out because it doesn't depend on n. So this is 3x minus 1 in absolute value times the limit as n goes to infinity of 1 over n cubed over n. But we already say that the limit of this is equals to 1 over 1, which is 1. So therefore, the limit of this is 3x minus 1 times 1. Now, the ratio test also requires, not the ratio, the root test also requires that the limit be less than 1. So therefore, we need also 3x minus 1 to be less than 1. So that implies then the minus 1 is less than 3x, less than 1, less than 1. Or if you add 1 to each side, okay, you have 0 less than 3x less than 2, or 0 less than x less than 2/3. Okay? And then these are the endpoints. So therefore here the radius of convergence is going to be still 1, because this number is 1. But for the interval of convergence, you know that at the very least it's going to be from 0 to 2/3. But you had to do the endpoints. And the endpoints this times it will be x equals to 0 and x equals to 2/3. All right, so notice that you use 0. This will be negative 1 over 3, which is convergent by the alternating series test. Okay, because this will be technically just minus 1 to the n over n cubed. So this should be okay for that. And this is equals to 2 over 3. So 2 over 3, well, let me do this one here. So notice you have 3 times 2 over 3 minus 1 to the n power. And notice that this will give you 1 minus 1, which is 0. So 0 is gonna always converge because it will give you 0 at that point. So therefore, it will work also for 2 over 3. So hence, in this case, it's just 0, so which is fine. So this is like a special thing. So therefore, the interval of convergence is going to be from 0 to 2 over 3. And that's it.